Good morning. Well, at least it's morning when I'm putting this up, putting this video up. What I want to do in this video is move away from Z intervals, which was the focus of the previous video. So this one, if we think about where we've been, sometimes it's kind of cool to talk about where we've been in context of where we're going. So previously, we've seen that we can use what's called a Z interval if we're going to estimate mu when sigma is given. But, a reasonable question, I think, is what do we do? What process do we use to estimate mu when sigma is not known or not given? And I will add that that usually this is the case. Well, what we do, guys, is we bring in a new type of distribution and a completely different type of interval, and we use what's called the t-interval key on our calculator, which depends on what we call the t-distribution. Now, just to give you an indication of what's going on here, let me just bring up the calculator real quickly and just show you that what we did previously is we used number 7, which was called the Z interval. Well, if you came on down just one more, you'll see the T interval. So from here on out, if you're estimating the population mean mu and the population standard deviation sigma is given, then you're going to go to this key. If you're estimating mu and the population standard deviation isn't given, then you go to your t interval. And you can really tell if you're in the right place if you understand your notation of your standard deviations, keeping in mind that the notation sigma stands for the population standard deviation, while Sx is the sample standard deviation. So if you got the standard deviation for your entire population, then you're going to use Z techniques. If you have the standard deviation just for the sample that you're analyzing, then you're going to use T techniques. And if you know the difference in this notation, it actually turns out to be pretty leading the way your calculator, because if we go into Z interval, look at the first thing it asks you. It asks you to put in the value of the population standard deviation. Well, if you don't have it, you can't put that value in. Whereas if we went to the T interval, you'll see that the first thing it asks you to do is to enter the mean, excuse me, guys, and the sample standard deviation. It doesn't ask for the population standard deviation because it knows you're here, because you don't have that. Guys, I don't know why. Excuse me. I'm losing my voice this morning, but take a drink of coffee here. Hopefully that'll quit that annoyingness. But anyway, your calculator, if you understand your calculator, it is very leading on what interval you should be, well, I should say what key of the interval you're using, because of what it asks you to do, okay? And all the other stuff is the same confidence level, same sample size, still got to put in your sample mean, and so on and so forth. So guys, let's learn a little bit about these T intervals if I don't lose my voice. Now, I'll tell you, I'm really struggling this morning. It's kind of dark out, it's kind of rainy, kind of dreary a little bit, but so the lighting here is kind of weird, so bear with me, because I kind of get tore up about stuff like that. All right, guys, let's talk about this Z interval versus T interval. What do we know about the Z distribution? Well, we know it's a normal distribution. There's one z distribution. And this z distribution has a mean of 0, standard deviation of 1. How does that contrast with the t distribution? Well, the t distribution is still bell-shaped and symmetric. But guys, it turns out that there are infinitely many t distributions. And, each of these does have mean 0, but the standard deviation varies according to the distribution that we have. But guys, in these t distributions, we don't worry about the standard deviation. We worry about what's called the degrees of freedom. Degrees of freedom is denoted by df. And I always joke it's really, really, really hard to find. It's actually really, really, really easy to find. All you have to do to find the degrees of freedom is take your sample size and subtract 1. So guys, if you're conducting a study where your sample size is 35, then your degrees of freedom is 34. Okay? It's actually that simple. Now, keep in mind that over here, to find, for example, like a z critical, we don't need to know the sample size. But over here, because the t distribution relies on the degrees of freedom, which lies on the sample size, we have to know the sample size to be able to create a t critical. So let me just go through that very quickly with you and show you how this works. So if we, for example, wanted to construct an 86% confidence interval, and the population standard deviation is known, then from the previous video, we would construct what's called a z critical. So we're doing an 86% confidence interval for an unknown mu, okay? Population standard deviation is known. We're going to do a z critical. So what would we do? Well, we do what I taught you in the previous video. We'd sketch out a normal distribution real quickly. We'd draw two lines, and we would put the number that we want to find that corresponds to the level of confidence that we want. We would put that in the middle. The next thing we would do is we would say, well, how much is missing? The next thing we would do is we would divide this by 2. Put half of that 14% in one tail, put half in the other tail. And we're just going to make sure that we have 7 plus 86 is 93 plus 7 is 100%. So these three numbers need to add up to 100%. To find this value right here, what are we going to do? Well, we're going to use our inverse z, which is called inverse norm. So we put the area below, which is 0.07. These things have mean 0, standard deviation 1. So negative 1.48 would be the value that we would have right here. Guys, because the mean is 0 and we have symmetry, we know that this would be positive 1.48. So the z critical would be equal to plus or minus 1.48. Now, let's change things. We want an 86% confidence interval. for unknown mu. The population standard deviation is not known. So we need now to find the t-critical, because guys, when we're estimating an unknown population mean and the population standard deviation is not known, which is typical, and guys, the t distribution is by far more commonly used in research than the z. But anyway, if it's not known, we use the t-critical. So how are we going to do this? Well, guys, we do the same thing. Draw two lines in the center. How much is missing? Divide by 2. All right. So now to find this value right here, what are we going to do in our calculator? We're going to use the inverse t key instead. Now the inverse t key only requires you to put in two things. It still has percent below as a decimal, just like the inverse norm. But here, because the mean is, even though the mean is still 0, standard deviation is not 1. Well, it could be in one specific distribution. Well, it's actually kind of a limit as sample size gets larger, but just forget what I'm saying. Okay? Because the only thing we put in here is the degrees of freedom. So the way this problem is actually given up here, we can't currently work it because we've got to have our sample size to be able to work the problem. So let's say, therefore, that up here that we know that the sample size is 35. So I would need to know that before I can work with the t-distribution. Okay? So guys, coming up with this, we're going to go to second function distribution instead of inverse norm, because the population standard deviation is not known. We have to go to inverse t. We need 0.07 below. Our sample size is 35. So our degrees of freedom is going to be 1 minus that. That's all we put in. We don't put in zeros and ones in the t-distribution. We just put in degrees of freedom. Well, that's just lovely. Well, yeah. Let's see if I can bring that back up. Well, my battery just went dead. Gosh, that was great timing. Let me see if I can find another calculator laying around here. Well, it's dead too. All right. Well, that's the beauty of being all geeky like I am. I got a calculator. Let's see if we can bring this up. All right, let's just use this one. So again, go second function distribution. Come down to number 4. And this actually gives it to you, a little differently, and it makes it very clear that you need degrees of freedom because it has df there. But nevertheless, the area is the area to the left, just as it is as we've done before. So we put in 0.07, and the degrees of freedom here are 34. Paste it into your home screen, hit enter, and the t-critical is negative 1.51. Now, if I did the other one, let's just show that we should know by now that it's going to give us the same value, except the positive. But if I did this other one, let's just think it through. What percentage do I have below? Well, I've got that 86 plus that 7, so I have 93% below here. So guys, if I was going to get the other one, which I think you guys all know by now that you don't have to do this. But if I put 0.93 there, degrees of freedom 34 paste, you'll see that I'm just going to get the positive of the 1.51. But because of symmetry, we know that. All right, so gang, what we know here is we know that the T critical would be plus or minus, well, I forgot. What was it, 1.51? Isn't that crazy? I can't remember what it was. 1.51. All right. Because usually I'm more clever than that, but, well, really I'm not. So anyway, so T critical is 1.51. So, guys, the formula, if you've been paying attention and you're with me at all, so, again, estimating an unknown value of mu when sigma is known. We can use the calculator. Or we can use the formula. That I showed you in the previous video. When sigma is not known, we use the T interval. Key in our calculator. And the formula is x bar plus or minus. But guys, instead of the z star, we have the t star. And instead of the population standard deviation, in this situation it's not known, so for obvious reasons we can't use it. But what would a reasonable person think we would use if we don't have the population standard deviation? Well, we would use the sample standard deviation. Because the sample standard deviation doesn't have as much statistical power. So we have to kind of lighten up the distribution that we use because of this substitution right here. Now, well, I was going to say something else, but I don't want to get ahead of myself and complicate things too much just yet. Now, I think the best thing to do now is just kind of jump in and get our hands dirty here and actually start working some problems, okay? So, first of all, let's review the z distribution before we jump into this t distribution, okay? So, the z distribution, at least currently, is used to construct a confidence interval for an unknown value of mu when the value of the population standard deviation is given. So we got a problem there. I'm going to just summarize it to you. The National Student Loan Survey collects data to examine questions related to the amount of money that borrowers owe. An administrator at a large university would like to use this information collected from a survey to estimate the mean student loan debt for all students at her university. A random sample of 1,280 students, so this must be an extremely large university. And if we did that at Shawnee, that would be a fourth of our student population. But, at like a University of Wisconsin that has, well, I don't even know what the population is there. But so anyway, their mean student loan debt was $28,900. So from the information, I know that the sample mean here is 28,900 and my sample size is 1,280 students. Now come on down and I read, results from a recent study indicate that the population standard deviation for all students who have student loan debt is 35,000. Because that standard deviation comes from everyone, I have sigma. I have the population standard deviation. So estimate mu, which is the mean debt for all students at this very large university, with 93% confidence. So the first question, why do we use the z distribution in this problem? Well, because we're estimating mu and the population standard deviation is known. Secondly, what is the z critical? Well, again, if we have 93%, we're going to play the same game we played before. Put that in the middle. I ask ourselves, how much is missing? Well, there's 7% missing. Put half of it here and half of it here. So guys, in my calculator, I'm going to use inverse norm because I'm using the z distribution. I want this as a decimal. And because I'm using the z, I'll use 0 and 1. All right? And I'm going to pop over here and get my calculator. And I'm going to use inverse norm. So I need 0.035. Mean 0, standard deviation 1. Paste that sucker, hit enter, negative 1.812. And I'm rounding to 3 places here. Not necessarily what you have to do. What you'll do is just make sure you round according to the way the question is being asked on your homework assignment. Now, when you get into an examination, it's going to be a multiple choice, so you don't have to worry about that. All right, gang. So you can see I put in the answer plus or minus 1.812 would be the z critical. Now, next thing says calculate and interpret the 93% confidence interval for the mean student loan debt for all students at this university. I don't know about you, but we got 2 options here. We can use the formula or we can use the calculator. I'm using the calculator. If I have the option and no one's standing over top of me telling me which way I got to use that or calculate that, I am going to use the easy way. First of all, it doesn't lend itself to silly arithmetic mistakes. So I choose the z interval because the population standard deviation is known. I don't have the numbers, I have the statistical results, so I need to select that. The population standard deviation is 35,000. The sample mean for these 1,280 students was 28,900. Sample size is 1,280. And we want to estimate with 93% confidence. All right, let's calculate it in our 27,127 to 3673. So I'm writing this stuff down. All right. All right, so that's calculated it. Now I need to interpret it, so we would say there is a 0.95 probability this interval contains mu, which is the mean student loan debt for all students at this large university. Now, it's pretty common sometimes when you're working a problem like this and you're interpreting to include the margin of error. Guys, remember margin of error is always plus or minus, and the easiest way to find margin of error is using the divide by 2 method, which is to take the big number minus the small number divided by 2. So let me pop over here and get the calculator. So the big number is 3673 minus the small number, which is 27127. Divided by 2. So 1773. So we have a 0.95 probability. Let me go back over. So I've just added that to the interpretation. So we're pretty sure with the point. Actually, it wasn't 0.95, was it? It's 0.93. Guys, by far the most commonly reported confidence level is 0.95. So I got sloppy here and just reported. In fact, most statistical software packages just give you 0.95 as the default. So that's the reason I got. I keep wanting to revert back to the 0.95, but your statistical, or I'm sorry, your homework online course management system mixes that up for learning purposes. So that's why I'm getting all tore up here, guys. All right, gang. Recall the t-distribution. Now we're going to get into the new stuff. I thought it was good to review something before we got here. Recall that t-distribution is used when estimating mu and sigma is not known. In cases where sigma is not known, we use a sample standard deviation instead. So here are a couple examples very similar to those from one of your assignments on Hawks. All right. The first one says, consider the value of t such that 0.12 of the area is to the right. Now this could be to the right or left, and I'll show you. Choose the graph. Well, I'm not going to choose the graph, but I'm going to show you what the graph's going to look like. So we're going to have this t-distribution, which looks like a normal distribution. We want the area 0.12 to the right, which tells me that 0.88 is to the left. So that's kind of what the graph is going to look like, 0.12 to the right of some t value. Okay. Now, part B says if the degrees of freedom equal 14, now degrees of freedom equal 14 tells me that our sample size was 15. Then select t value from the t table. Guys, I don't use tables. I use the calculator. I'm anti-table. Told you that early on. Shoot, my coffee's cold. That's not cool. But anyway, gang, what we'll do is we'll go to our calculator. And we'll use the inverse t. Our area to the left is 0.88. Even though the problem gives us 0.12, we always have to put area to the left in our calculator. Our degrees of freedom is 14. And our value is 1.227. All right, so I wrote that down. So this is the t critical. Those of you that don't have a calculator, let me bring up R and I'll show you how you can do that in R. It's really, really easy. What you use here in R is you use what's called QT. You still put the area to the left and you put the degrees of freedom. And you'll see that you get 1.227, exactly like you did with the calculator. So R is kind of cool because R works very quickly and it's very easy. And it works just like the calculator. Instead of using inverse T, you just use QT. Now, some of you, I should have mentioned this early on, some of you may have an older calculator, maybe a TI-83 or something, and maybe this isn't showing up. Let me show you what you can do to get this, and it's really easy to do. If you will go to YouTube, and if you'll just type in inverse T, and just hit enter. The very first thing that comes up is programming inverse T into a TI-83 or TI-83 plus calculator. All right? Now, you don't need to worry about this if your calculator, when you go second function distribution, if you come down and see inverse T, you don't even need to worry about this. But if you're one of those people, and I guarantee you there are people in our class who don't have that inverse T option, then you need to listen very closely. If you go to YouTube and play this, all right, it's a 12-minute video. You don't even need to get into the preliminary stuff, just going through and get to the good stuff. And it's going to go through how to, well, it's not one to play, but anyway, it'll play on yours. So it'll tell you how to program. It'll tell you. I got ahead of myself here, but it'll tell you exactly what keys to hit to program this into your calculator. Guys, it works. It's going to take you about 10 minutes, but it's going to be much, much, much easier than those goofy tables that some people like for you to use. Okay. So, guys, there's an option. It's going to take you a little longer, but it's not a big deal. Just take time away from Facebook and Twitter and all that cool stuff, But guys, you can do it. Students are doing that. Have done that all the time in my classes. All right, gang. Let's look at number 2. This is another type of question you're going to run into on Hawks, and it's a little bit more confusing because it gets into this scientific notation stuff. So consider the value of T such that the area under the curve between negative T and positive T equals 0.60. Now guys, all that's saying is we have our T distribution, and we have from negative T to positive T, we have 60% of our area under the curve there. Well, the graph would just be this, but again, it's the same game we played before. How much are we missing? 100 minus 60 is 40%. Half of it here, and half of it here. Those three numbers have to add up to 100 because the area under the curve is 1 unit or 100% of our population. So that's what your graph will look like. Now down here it says if the degrees of freedom equals 14, then select the T value from the T table. Well, I don't use T tables. Again, I use the calculator. So I can find this value right here by doing what? Finding what has 20% to the left of it when degrees of freedom are 14. So guys, if I want to use my calculator, I can do inverse T. The area to the left is 0.2. Degrees of freedom still 14. And I get minus 0.80, well, let's just say 0.868. So the T critical is going to be plus or minus 0.868, depending on how the technical accuracy that the question is asking you to put your answer in. All right, so guys, if I needed to do this What's going on? Why is R not showing up? Here we go. So if I want to do the same thing with R, which is again is free, so we get the same answer. It'd be kind of wacky if one statistical software gave us one answer and the calculator gave us something else. So that works the way it should. All right, boys and girls, we're about done with this video. Let's just work a couple of problems. All right, computers in a specific type of vehicle calculate fuel efficiency by reporting the miles per gallon. I know mine does. Manufacturers of this vehicle would like to use measures from the following random sample to estimate with 84% confidence the mean miles per gallon for all of their vehicles of this type. So it looks like they took 7 numbers. They took 7 measurements, 7 cars, drove it I'm sure on the same road, and they got some variation in their miles per gallon, which you would expect. So part A says calculate the mean and the standard deviation for this sample. Well, guys, that's going to be easy. All right, so you may want to pause and write these numbers down. I'll tell you what I'll do. Let's do some fancy stuff here. Not really, but all right. So I've got split screen going on here. So guys, if I want to find the mean and standard deviation of a set of data, I'm going to go up and I'm going to hit clear enter. And I'm going to very carefully type in my data. So 41.5, 39.8, 37.2, 40.8, 42.2, 39.9, and 38.1. All right, gang, I would go back and check 38.1, 39.9, 42.2, 40.8, 37.2, 39.8, and 41.5. Okay. So guys, to find the mean of and standard deviation, I'm going to go to stat. I'm going to go over to calc, one variable stats. I put my data in L1. I don't have a frequency distribution. So I hit calculate, and I see that my mean is 39. Let's see, what does it say? It says report these to one place. So my sample mean is 39.9. And my sample standard deviation is 1.8. Okay, because I use SX. Now, let me tell you what a lot of students do. They'll look up there at their calculator and they'll see that sigma x and they'll think, well, my population standard deviation isn't known. If you can justify that this, based on the context of this problem, that this manufacturer would only be able to calculate 7 at most measurements, then you might make an argument to use sigma, but long story short, we never use that. You will never, ever, ever in my class use that 1.65. You will never, ever, ever, ever use the value that goes with sigma x on your calculator. If you're calculating with your calculator, if sigma is given in the problem, use it. But if it's not, you're forced to use SX. All right, gang. Find the critical value that should be used to construct the confidence interval. Well, it looks like we're going with 84%. So, gang, use the same old, right? How much is missing? 16%. Half of it here. Half of it there. So I need, I have, in this situation, Notice that I have n equals 7. So my degrees of freedom are equal to 6. So I'm going to go second function distribution, inverse t. Area to the left is 0.08. Our degrees of freedom 6. So my t critical is going to be plus or minus 1.603. Now the next thing says calculate the 84% confidence interval using the formula. All right, now I'm going to get out of here. Well, yeah, I just understood here. So the 84% confidence interval here, we're using the t-distribution because the population standard deviation isn't known, and we have the sample standard deviation. So I'm going to use x bar plus or minus t critical, the standard deviation over the square root of n. So guys, I have a sample mean of 39.9. Plus or minus the z critical is 1.603. The sample standard deviation is 1.8. And I have 7 observations, 7 measurements. So if I can put that in my calculator without doing something goofy, you know, guys, remember, we don't put the degrees of freedom there, we put the sample size. Now, I see a lot of students say, well, we'll put degrees of freedom there. That says N, it doesn't say DF. All right, hit enter. Beauty of the calculators, I can go second function entry when I have something that I'd like to come over here, it's taking forever. Let me change that to a plus. All right, gang, so my confidence interval is going to be 38.81 to 40.99. Now the next thing says calculate the 84% confidence interval using your calculator and the t-interval key. Well, it's kind of cool when you can do this because it's really easy. And you can do this. No reason you can't. It's the reason I had you buy this $1 million calculator. Now here's a situation where I have my data typed in my calculator, so I'm going to use that. And I'm going to tell the calculator that I put my information in L1. And I'm going to tell the calculator that I want it to calculate an 84% confidence interval. And you'll see that we get 38.85 to 41.01. Now, guess why the difference? Well, the difference is we rounded this to 1.603. Now, let me show you a way. It's a little complicated. This answer is best. Because this one used an approximation of 1.603 plus or minus 1.603. Let me show you in your calculator how to get this without doing a whole lot of typing. And I can just I can go back and get. So if I wanted the answers to come out exactly right, I can do inverse t. We saw that 0.08 and degrees of freedom were 6. And I can paste this. And I get my answer. Now what I can do here is kind of cool. I can take the answer times a -1. And I can store that as x. Now what I can do is when I come back over here and I use this formula, I can just put an x there. Because what x has done is it has stored the entire 1.60325124.8 and so on and so forth. So I can type the 39.9 minus x times 1.8. And guys, it's going to be off a little bit still because 1.8 wasn't exactly the standard deviation. Square root of 7. Hit the right arrow to get out of that. And we're going to get a little bit better 38.81. Well, it didn't help at all, did it? And the reason is because my mean is approximated at 39.9 and my standard deviation is approximated as 0.8. So let's see if there's a way that we can take care of that. I think there is. If we go to variables and go to 5, we can come down to number 2. Let's see what this does. Let's see if it gives us. Yeah, it does. So let's do this. Let's go to variables. You're probably sitting there thinking, Dr. Darber, why don't we just use the... So let's go x bar minus. Now we can use our x thing times. Now let's go get the standard deviation, which is at number 3, divided by the square root of what, 7? Now, well, shoot. All right. Now, notice how we get 38.845 exactly like we got right here. So 38 point, and then if I do this again. So the main thing, I don't really know if you'll want to go through all this to work your problems, but the main thing I want you to know at 41.01, which is what we have right here. The main thing I want you to know is that rounding off this to one place and this to one place and this to 3 places gives us an approximate answer on our confidence interval. This uses the mean completely, the standard deviation completely, and the t-critical completely when we use our calculus. So anyway, I want to show you, point out why we have that discrepancy. All right, so number 4 says the normal range of values of blood phosphate levels is 2.6 to 4.8. A randomly selected patient who is on dialysis is given 6 blood tests. His mean blood phosphate level is 5.37 with a sample standard deviation of 0.67. Calculate the 95% confidence interval for this patient's mean blood phosphate level. Is there a reason for concern that his blood phosphate level is too high? Well, gang, I'm going to use the calculator. I'm going to go down here to the t-interval because when I read the problem, I realize that the population standard deviation is not given. I don't have my data. I have the statistical results. It says the mean is 5.37. The problem gives us a standard deviation of 0.67. It says that this person took 6 blood tests. And we'd like to estimate with 95% confidence this person's average blood phosphate level. So this person's blood phosphate level looks like it's 4.7 to 6.07. Now, is there a problem for concern? Statistically speaking, there's not, because a normal range of values runs from about 4.7 to 6.07. This person's confidence interval ranges from 4.7 to 6.07. No, wait a minute. What am I talking about here? I have no idea what I'm doing. I'm getting all messed up. The normal runs from 2.6 to 4.8. I tell you, that's driving me crazy. I can't do that. Too picky for that. So, all right, so normal runs from 2.6 to 4.8. And this person's confidence interval runs from 4.7 up to 6.07. Because of that overlap right there, because there's a 0.95 probability this person's mean blood phosphate level falls between 4.7 and 6.07. Because of that overlap right there, statistically speaking, we couldn't determine this person has a mean blood phosphate level that's higher than 4.8. We can't determine that statistically. Is there kind of a empirical common sense concern? I think so. This person's mean was 5.37, which is above the 4.8. But statistically speaking, we can't determine this person has, we couldn't conclude. Now, first of all, major concerns here. First of all, N is too low. Only 6 measurements. I'd want to bump that up to at least about take 30 measurements. If I wanted to statistically conclude, I would want to bump this up to about 30. Because central limit theorem tells us that we need a sample of 30 to make sure we have a normal distribution. So, but guys, based on the 6 measurements, we can't conclude statistically that this person has a blood phosphate level that's above the range of 2.6 to 4.8 because of the overlap. All right, guys, we're going to get into something called a hypothesis testing, which will give us a formal procedure to test that, but more about that later. So, guys, have a great one. I'll be back at you soon.